Hello everyone and welcome back to Diksha Karnataka YouTube channel, and currently you are watching KCET 60 out of 16 physics series, where we are discussing each and every chapter topic wise, concept wise. We are breaking down every detail of the chapter. Today I am here with a new chapter, Electromagnetic Induction. This is a small chapter but very important chapter. Every year 2 to 3 questions coming from this chapter, so don't ignore this chapter. This is an easier chapter, okay, and most importantly many concepts from this chapter are not deleted, so you can find most relevant questions from this chapter. So this is going to be a one shot chapter. Here we are going to discuss entire chapter in this video. Okay, there will be no parts for this chapter as the concepts given in this chapter are very limited, but questions are not limited. Questions can come from this chapter based on multiple concepts, some from the previous chapters, and also we will see how we are going to solve them. So let's start. Before also you have to join our WhatsApp group. Day after tomorrow you will receive our KPL mock test 4 for physics, okay, match number 4. So if you are participating in KPL, don't forget to join our WhatsApp group if you have not yet joined, and you will get the question paper of KPL on our WhatsApp group. The link will be given in our WhatsApp group. You can download the question paper, solve it, and Sunday evening I'll be back with the answer. So don't forget to join our WhatsApp channel if you are participating in KPL, and it is absolutely free, without any cost, without any charge. KPL is free for everyone, okay, and it is for your preparation. Also I mentioned yesterday's lecture that this week's KPL will be based on moving charges and magnetism and matter, these two chapters. So electromagnetic induction I have not included in this week's KPL, but it will be there in next week's KPL, so don't worry. And this is a very important chapter, that's why I am saving it. I will discuss more about the previous year questions in tomorrow's lecture. Okay, now let's start with the obviously the list of contents. What all we are going to discuss in this part? We are going to discuss electromagnetic induction, then we will be discussing magnetic flux, then we will discuss Faraday's law, very important, then Lenz's law, another Lenz law is also very important, then motional electromotive force or motional EMF. Okay, electromotive force is nothing but EMF that we call in short. Then we will talk about inductance. In inductance we are going to talk about self-inductance as well as mutual inductance, and last but not the least we will going to be talk about AC generator. Okay, now let's move on to first electromagnetic induction. Okay, electric currents can be induced in closed coils when subjected to changing magnetic field. So I have a closed coil. Suppose I have a closed coil, okay, with a galvanometer fixed on this coil, okay, and if I change the magnetic field field lines linked with this coil, then there will be some so if I change the magnetic field associated with this coil, then there will be an induced current in this coil. This is called electromagnetic induction, the phenomena in which the electric current is generated by varying magnetic field is called electromagnetic induction. Obviously induction means when you are inducing something without directly touching it, right? Suppose I am teaching you, I am asking you to do some test, I am asking you to do some exercises. So if you are adapting to that, I am not directly touching you, but if I can induce some good behavior, some good practices in you, then I will be a good teacher. So job of a teacher is induce good practices, good teachers, good habits among students. That is called induction, right? Now let's move on. Another important point is magnetic flux. If you remember, we have learned something similar in electrostatics about electric flux, but that we learned during Gauss's law. But here Gauss's law we have already completed, right? Because for magnetic field there is no monopole, so magnetic flux through a closed surface is always zero. Not magnetic flux, total electric field in a closed surface is always zero. Magnetic field in a closed surface is zero, but here we are talking about magnetic flux. Suppose there is a magnetic field lines crossing a surface, okay, similar to that of electric field. Okay, everything is very similar to that of electric field. Everything is similar. Now magnetic field is crossing at some angle with the surface. The surface makes an angle theta with the surface. Then magnetic flux can be written as phi b equals to b dot a or ba cos theta, similar to that of electric field. In electric field it was only phi, we mentioned only phi for electric field. It was e dot a and it was ea cos theta. Everything is similar, same as magnetic flux, okay, but magnetic flux plays a major role in electromagnetic induction than Gauss's law. In case of electric field, electric flux was mostly relevant for Gauss's law of electrostatics. But in case of Gauss's law, there was not much importance of this flux. But this flux plays a major role when we are talking about electromagnetic induction. We will see how it's so. Okay, first of all, let us solve the homework problem from yesterday's class. A paramagnetic substance of susceptibility 3 times 10 to the power of minus 4 is placed in a magnetic field of 4 times 10 to the power of minus 4 ampere per meter. This is very important. This unit is very important. Okay, then the intensity of magnetization. So what they have asked you to find capital M. Now susceptibility, we know susceptibility is given by chi equals to 3 times 10 to the power of minus 4, right? Now they have asked you to find the intensity of magnetic field, that is M. Now here magnetic field is given not in terms of Tesla, okay, normal unit of magnetic field is Tesla, okay, but it is given in ampere per meter. Ampere per meter means basically magnetic field intensity or capital H is given. Okay, so be careful when you are dealing with these things, okay, when you are dealing with such things, because they will change the unit and they will call this is magnetic field, and this is from one of the latest year questions. Okay, I think 2023 or 2022 this question came. So they will just simply change the values and they will say find it. Now we know that M is basically chi H, right? So that's how we substituted in the formula and calculated the relative permeability, right? So here what we have to do, we simply just need to multiply these two values. Okay, 3 4s are 12 times 10 to the power of minus 4 minus 8, okay, ampere per meter, right? Now since this is unitless quantity, so we don't need to worry about it. It is ampere per meter, right? So the magnetic intensity is 12 times 10 to the power minus 8. Now there was a minor mistake in yesterday's homework question. I missed this negative sign, but in the power it will be negative sign. Unfortunately, none of you have able to answer that question. Now let's move on. It was not yesterday, it was day before yesterday, because yesterday was PYQs we have done. But day before yesterday we have completed the chapter and I gave these two homework to you. Now next let's look into the second homework problem. Relative permeability of a medium is 0.92. What is the magnetic susceptibility? So they have asked you to find the susceptibility, and relative permeability means mu r is given. Now if you remember what is the relationship between mu r and chi, mu r is basically chi plus 1 or 1 plus chi, whatever you can say. That's how we defined it. So chi is basically mu r minus 1. Okay, so basically 0.92 minus 1, that is 0.08. Sorry, not 0.08, it is minus 0.08. Now they may ask you, this question can be changed, okay, that what is the type of this material? Okay, what is the type of this material? This is a diamagnetic or paramagnetic or ferromagnetic or any of this or none of this. Okay, what type of material is this? So basically they are not asking you directly, but they are asking an indirect question. First of all, you have to calculate the chi, and chi is negative. Okay, chi is negative, that means it has to be a diamagnetic material, right? Because we know that it is slightly negative for diamagnetic, slightly positive for paramagnetic, right? And it is very high value for a ferromagnetic, right? So but the value here is small, but it is slightly negative, so we can say this is a diamagnetic material. So this is an alternative version of this question. Now let's go back to these are very small questions, so we have completed the homework. Now let's go back to our discussion of today. Faraday's law of induction. An EMF is induced in a coil when magnetic flux through the coil changes with time. Now previously we are talking about when we are changing the magnetic field associated with the coil, there was some induction. Now here we are specifically saying that it is changing when magnetic flux, okay, through a coil or through the coil changes with time. Okay, it should not be a spontaneous change, it should be changing, it keep on changing with time. Later on we will see how we can accomplish that, how we can keep on continuously we can change the flux linked with the coil. So that there are different methods. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Okay, so the magnitude of the EMF induced. EMF means electromotive force. Okay, so magnitude of the EMF is directly proportional to d phi by dt. Okay, or d phi b by dt. Okay, d phi b means magnetic flux. There is a negative sign. We will explain the negative sign in a while. So here we have one coil. Okay, here we have one coil and there is a magnet. Okay, now you are taking this magnet towards the coil. You are taking this magnet towards the coil. So what is happening? The field lines, okay, which are coming out of this magnet, okay, they are changing, that is crossing this cross section, right? So field lines crossing this circle is changing each and every second. So what you are doing, you are holding this magnet and you are taking it towards the circle. For at some point, okay, suppose the magnet is now here. Magnet now reached, suppose the magnet reached a closer position. Now what will happen? More number of lines will pass from the magnet, right? So number of field lines is increasing. Number of field lines increasing means magnetic flux is increasing, right? B dot A is increasing. So we can say there will be an induced EMF. Similarly, if you take this magnet away, in that case also what will happen? Initially the number of lines was more, but finally the number of lines is less. So initially the flux was high, finally the flux is less. So flux is changing. Flux changing means there will be an induced EMF. Okay, and always we will use this formula to calculate the induced EMF. Okay. Now, in case of closely wounded coil of n number of turns, so in this case, suppose only one coil was there. Here we have shown that, see, 1, 2, 3, 4 coils are there. But if only one coil was there, then this would have been the formula. Okay, for only one coil. Okay, but instead of one coil, if there are n number of turns, for example, here 4 turns are shown here. Okay, n turns, change the flux associated will be given by this formula. Only simple thing, you have to multiply with this n. Okay, just need to remember d phi by dt minus d phi by dt is the EMF associated with single coil, and if you multiply with n, that becomes the flux associated with the coil. Okay, because coil generally has more than one turns. Okay, loop means one. Okay, coil means multiple loops, right? So when n number of turns are associated, the formula becomes minus n d phi b by dt. Okay, now let's look into one problem that based on previous year questions. A magnetic field of flux density 1.0 Weber per meter square acts normal to a 80 turn coil. Okay, 80 turn coil of area 0.1 meter square, 0.01 meter square. This coil is removed from the field in 2 seconds, the EMF induced. So magnetic flux density is given. Flux density means what? So density means, now we have to check the units. Density is given in terms of Weber per meter square. So flux generally calculated in the unit of Weber. Okay, that is also important. So flux density is flux divided by area. Okay, flux divided by area, okay, is given by 1.0, right? This is nothing but actually magnetic field. Okay, flux density is sometimes also called magnetic field. Okay, we know that phi is equal to B dot A, right? So B A cos theta, here cos theta is 1. So in such a case, we represented it using flux density, right? Because the cos theta component we have, if we take the cos theta component included in this area, then that becomes flux density, right? So don't worry too much about this flux density term. Flux density is nothing but flux per unit area, right? So flux is basically phi B. Phi B is basically this value times area. Now what is the area? Area is given 0.01. So 1 times 0.01, that is 0.01. Okay, so flask we have calculated. This is the change in flask. Now this much flask is changing, okay, in 0.2 seconds, 0.2 seconds, right? This much flask changes, okay. So we can write this as d phi, okay, d phi b, okay. Because if you remove the coil from the circuit completely, the final flask will be 0. Initial flask is this, final flask is 0. So change in flask is this minus 0. So this you can write as d phi b. Now the time given is 0.2 seconds, right? Now we know that induced EMF is magnitude wise. We do not take the negative sign when they have only asked you the find the induced EMF, okay, value of induced EMF. We generally do not consider the negative sign. So now let us put the value N d phi b by dt. Simple. So N is 80, d phi is 0.01 and dt is 0.2, right? So one decimal goes from here, another decimal still remains, so it will be, and 2 becomes 40. So 40 times 0.1, that is 4 volt. Everything is in SI unit, so the final answer will be 4 volt. So the correct answer is 4 volt. So be prepared for such problems. Be prepared for such problems where they will ask you, you are changing something, flask is changing. You have to calculate the change in flask first, then the time will be given to you, then you have to find the rate of change of flask. Be sure you have a grip on this type of questions. Now let's move on. Now let's look into Lenz's law. What is Lenz's law? The negative sign that was coming into the Faraday's equation, that negative sign was initially not there. When Faraday gives his law, at that point of time, Faraday says, if you read the law correctly, Faraday says epsilon is directly proportional to d phi by dt, right? Now Lenz, another physicist at that point of time, he came and he said this cannot be 100% correct, there has to be some restriction on this. So what he said, the polarity of the induced EMFs is such that it tends to produce a current which opposes the change in magnetic flux that produce it. Okay, so this is the Lenz's law. Now one time I think in a PU board question, this question was formed, this statement was given, and then they asked is whose law it is. Lenz's law, Faraday's law, Coulomb's law, Gauss's law. So you have to correctly identify this is Lenz's law. Lenz's law basically states that the EMF that induced, now as we know, when there is a current passing through a coil, that coil also becomes a magnet, solenoid for example, we have learned that, right? If there is a current passing through a solenoid, mu naught Ni, right? So mu naught Ni is the induced, mu naught Ni is the current, magnetic field produced by that current passing through that solenoid. Now what is happening here is, there is a solenoid basically. but the solenoid is not connected to any external electric source. That current is being produced by this moving magnet, right? So the moving magnet is trying to move towards the coil, so the coil will also become a magnet now. Now what will happen? This magnet and the original magnet, that magnet is coming towards it. How they will react, how they will attract each other or they will repel each other. That is the question. From there Lenz come to this conclusion that the polarity that is produced by this magnet, this induced magnet, we call this induced electromagnet, right? So this induced electromagnet, the polarity should be, it is such that it opposes the motion of the original magnet. How? Suppose I have a north pole, I am moving it towards the coil, okay, the coil will produce the current in such a way that there is a north pole developed in this end. Okay, now this north pole and this north pole, what will happen? They will repel each other. So you have to force this magnet. This is not easy. Okay, you have to force this magnet. As fast you try to move, more stronger will be this magnetic field. Okay, so the induced magnetic field will be stronger if you try to do it very quickly, but if you try to do it slowly, then the induced magnet will be less effective, right? So why this is happening, I will explain it in a while. Similarly, if you take a north pole and if you try to move it away from the coil, okay, in that point of time this will become a south pole, so that it opposes the motion. Okay, so that when the magnet is going away from the coil, okay, this will become a south pole and it will try to attract that north pole towards it. Okay, so every time a magnet is moving near a coil, the magnetic field induced in this coil will try to oppose the original magnetic field, the source of this current. Okay, so this coil does not want to be disturbed. Okay, this coil wants, I am simply a coil, do not disturb me, you are disturbing me, so go away. Okay, so this coil is trying to move this north pole away from this. Similarly, this south pole is saying, why you are going away, come back and stay where you are. Okay, so this coil is going away, so this south pole is trying to attract it and saying, okay, wherever you were at that beginning, stay there, okay, don't move. So that is how it works, if you remember that, and this is a direct consequence of the conservation of energy. That's what I said. The reason behind this is conservation of energy. Now just give me a small example. Suppose this north pole is moving towards this coil, and somehow instead of a north pole, okay, there is a south pole. Okay, so what will happen? You just push this magnet. You push this magnet by small amount, so immediately there is a south pole and this is a north pole, so they will attract each other and this north pole will automatically start moving towards this coil, right? If this was not true, obviously we are assuming that Lenz's law is false, Lenz's law is not correct, then what would have happened? Suppose instead of north pole I am trying to move this coil away from this and there is a south pole developed somehow. So what will happen? This north pole will get attracted towards this coil without any help or without any external work being done on this coil, on this magnet, right? So what will happen? This coil will start producing current, right, automatically without doing anything. Initially you just pushed it by for say 1 second. After that this process is continuing without any external work, without any external money being produced. So what is happening? You are producing current out of nothing. You are producing current energy, which is a form of energy, out of nothing, which is not possible according to the conservation of energy. According to the conservation of energy, you cannot produce anything out of nothing. Right? So basically this is prohibiting the source to produce unlimited power. Okay, so Lenz's law is very important because it was the first thing that he said that this cannot happen automatically, this cannot be continuous. Okay, so that's why he said that this must be correct. So this must prohibit the original source to produce more current. That's how we have to do external work. If we want to continue production of the current, then we have to continue doing external work. That's how the work is being converted into electrical energy. Now, another important thing, Okay, this is motional EMF or motional electromotive force. How this works? Suppose we have a magnetic field. Okay, a magnetic field, a region of magnetic field. Okay, all the electric fields, magnetic fields are going into the page. Now I have a frame like structure. Okay, one frame is like that. This is complete very long frame, and I have a rod placed on this frame. This frame is open on right hand side. Okay, it is closed on the left hand side, it is open on the right hand side. Now I take another rod, loose rod. Okay, I place it on top of this frame. Okay, I place it on top of this frame. You can imagine this frame to be like a rail. Okay, like a railway. Okay, this is but one side of the railway is closed, other side of the railway is very long, and this rod can move along the tracks of this railway. Okay, now if you take this rod and move it towards this side or this side, does not matter. If you move this rod, okay, with a velocity, constant velocity v, then what is happening is that the number of field line passing through this active region, this is we called active region, this is a closed region, right? The number of field lines passing through this closed region is changing. Okay, in this case number of field lines is decreasing. If you take in this side, number of field lines is increasing. So what is happening here is, when this rod is trying to go from this side to this side, okay, there will be a EMF developed in this circuit. Okay, so what is happening here is, this rod will be a source of a battery. So you can say this is a negative polarity. Okay, this side will become negative, this side will become positive. Okay, there will be an EMF developed between these two sides. Okay, there will be an EMF developed between these two sides. Now this EMF developed between these two sides is called motional EMF, because we are changing the flask associated with this coil, with this circuit. So that is being produced due to this motion. Okay, if you stop this rod, there will be no more motion, right? If you pause this rod, the field lines crossing this area will be constant, flask will be constant, because flask is B dot A. So B is constant, area is constant, and flask is constant, so no flux change. D phi is 0. D phi 0 means epsilon will be 0. Now what is happening here? B is constant in this case. We are changing the area. So B dot A. So A is changing. A changing means D phi will be changed, right? D phi will not be 0. So D phi will there will be a value for D phi. So based on that direction of motion, for example, in this case, when the rod is moving in this direction, okay, the original motion of this electric field will try to stop this motion. So there will be a positive side in the below and negative side in the top. Similarly, if you move this rod in this side, okay, in that case there will be a positive in the top, negative will be in the below. Okay, just to identify the polarity, you need to remember how this is happening. Okay. Now, the magnetic flask phi b enclosed by the loop PQRS. So, PQRS, the magnetic flask associated with this will be given by BLX. Now, what is B, what is L, what is X? So, B is the magnetic field, which is a constant. B is constant, right? Now, what is L? L is the length of this rod. Okay, length of this rod. Okay, and X is the width. Okay, now we know that area is length into breadth, right? Length into breadth, that is the area of a rectangle. So L times X is the area of this LX. LX is the area, right? LX is the area, and B is the magnetic field. So phi flask associated with this will be BLX, right? So B times A. Now, since X is changing with time, the rate of change of flask phi b, the rate of change of flask phi b will be induced an EMF, and it is given by d phi by dt, okay, equals to B. B is constant. Okay, the length of the rod is constant. Only thing which is changing is X, right? It is moving in this direction, so only thing is changing X. Either it is increasing or decreasing based on which side it is going. right? So d phi by dt is equal to BL dx by dt. Now what is dx by dt? Dx by dt is nothing but the velocity of the rod with which it is moving, right? We know that dx by dt is velocity, so we simply write this as we can write the induced EMF epsilon naught directly as BVL or BLV. Okay, whichever way you can remember, this formula is very important. Okay, many a time similar questions come from this topic. Now let's look into one such question. A metallic rod of length 1 meter held along east-west direction and is allowed to fall down freely. Given the horizontal component of Earth's magnetic field is 3 times 10 to the power of minus 5 Tesla, the EMF induced in the rod at an instant t equals to 2 seconds after it is released. So what is this? So you have a rod east-west direction, okay, and you released it. Okay, so it is falling downward. Okay, now when this is falling, okay, there is a magnetic field associated with this horizontal component. Okay, horizontal component is not in this direction, sorry. Now horizontal component itself is no longer part of the syllabus, but this question may come. Remember this, okay, because they might say it is falling in a magnetic field in the perpendicular direction with these values. Okay, so what you have to do, you have to only do BVL. Okay, epsilon is equal to BVL. Simple one formula. Okay, so instead of B, they have given BH, which is same. So 3 times 10 to the power of minus 5. Okay, V velocity is given, velocity is not given, length is given 1 meter. Okay, velocity is not given, so we have to calculate the velocity. So how we have to calculate the velocity? It is falling. So one object is falling under gravity. So acceleration of gravity is g. So after some time t, what is the velocity? Velocity will be gt. Remember that v is equal to at. U plus at, u is 0 in this case. Initially it was at rest. So u plus at, here instead of a it is gt. Okay, and u is 0. So g is 10, t is 2. So 20 meter per second is the velocity. So you have to put the value here 20 and L is 1. So what we will get, 3 to the 20, 3 to the 60, sorry. Not 3 to the 60, 3 to the 6. Okay, 3 to the 6 and 1 0 we will compensate here 10 to the power of minus 4. Okay, so the induced EMF is 6 times 10 to the power of minus 4 volts. Okay, 6 times 10 to the power of minus 4 volts. So even if you drop a simple rod of 1 meter length, there will be some EMF induced in that rod. But if you, as you see, this value is very small because Earth's magnetic field is very weak. So this is not very useful for us to produce any useful current. Okay, so basically what it says that you can automatically produce current by simply dropping one object. But that current, that voltage is very small and that is not usable. If to produce some meaningful current, you have to increase the length of the rod, which is not possible. Okay, you have to make it very large. So that is very difficult for us to obtain, right? So that's why this method is not used. But there will be some EMF induced. So when we are designing very high costly equipments, for example a plane or some satellite devices, okay, they suffer minor setbacks because of even this small amount of voltage. So they have to be designed such a way that they can withstand this much amount of voltage. Okay, so this is one of the practical application. Now let us talk about inductance. Very important concept, inductance. What is the meaning of inductance? Suppose we have two coils. Okay, in one coil we have, it is closed and there is a galvanometer connected. In another coil we have a variable voltage source. So variable voltage source means I can change the current through this coil. Okay, now if I change the current through this coil, I know that this is a coil. So this coil will have a magnetic field at this point. Suppose this distance is x. this distance is x, then we know that there will be a magnetic field due to this coil at this point P, okay, and that field is given by mu naught Ni r square divided by r 2r square plus x square to the power 3 by 2. I hope you have remembered this formula by far so far, because this formula is being used so many times. So I think you have already understood this formula. Now this magnetic field is produced here due to this coil. Now if I change this I, if I vary this I by changing the voltage, V is equal to IR, right? So if I change voltage, current will change. So if I change this current by changing voltage, okay, the magnetic field will change at this point. So magnetic field is changing means what is changing? Magnetic field times area is also changing. Area is constant in this case, but magnetic field is changing, but magnetic field times area will also change. So flask will change. So flask is changing means there will be a induced current in this case. Very important. Okay, so by only changing current, now we do not need magnet. Okay, in fact, if you have never seen any magnet moving around us, but we can still produce current in many cases. So why it is happening? Because we are just simply changing the current, and that changing current is inducing a secondary current in this case. Now how these two changing currents will be linked to each other? So an electric current can be induced in a coil by flask change produced by another coil in its vicinity, or flask change produced by the same coil. So basically what it says that this coil can change the flask linked with this coil, right? Another way of thinking is this coil itself is producing a magnetic field. Okay, that magnetic field, if I don't consider there is another coil is here, for some time assume that there is only one coil. Okay, now I am changing the voltage, current is changing. Current is changing means the magnetic flask linked with this same coil, single coil, is also changing, right? So changing this magnetic flask linked with this single coil can also change the current that is flowing through it. Okay, that is very, very important. Okay, so basically what is happening, I am doing some work. That work itself is trying to stop me from doing the work. It's like that. Okay, you can say this is kind of, we will explain that in a while. Now the flux through this coil is proportional to the current. Okay, so whatever flask is associated, maybe flask associated with this coil or flask associated with this coil, everything is dependent on only one thing, that is current, right? So we can say that flask is basically directly proportional to current I, right? Or the change of flask, the rate of change of flask is directly proportional to rate of change of current. We'll see that in a while. Now let us talk about two different cases. First is mutual inductance, the first case where we are talking about two coils. Let us consider two long coaxial solenoids S1 and S2, each of length L. So now we are considering two coils. One coil is like this, another coil is through the center, though both coils are coaxial. That means they are passing through the same axis. So whatever, suppose you are passing a current through this inner coil, then there will be a flux change in the outer coil, and if you change pass a current through the outer coil, there will be a flux through the inner coil. So both coils are interlinked, and for at a time you are passing a variable current through only one coil, and you are trying to measure how much current is induced in the second coil. When a current I2 is set up through S2, so what they are doing, first they are setting up a current through S2, that is the outer coil. Okay, it will then set up a magnetic flask through S1. So as I said, when I am sending a variable current through this coil, okay, there will be a magnetic flask. Now that flask will be linked to the inner coil as well, because it is sending flask in all the possible direction, right? Now if we denote this flask by phi1, then N1 phi1 is equal to M12 I2. So we are changing the current. This is I2. Okay, so the current through this outer coil is I2, and then the flask that is linked with the inner coil, say phi 1, that should be proportional to I2. Okay, the number of turns time phi 1 is equal to M12 I2. Now what is M12? Here M12 is called mutual inductance of the solenoid S1 with respect to solenoid S2. Okay, this is called a mutual inductance. A new term. Now this is for S2. Now the same thing will happen if I change a current through S1 as well. So let's look into that. Similarly, a current I1 is set up through S1. Now if I set a current, say I1 through S1, okay, in turn it sets up a magnetic flux through S2. Okay, let us denote this by phi 2. Then N2 phi 2 is equal to M21 I1. Okay, now this is the mutual inductance of the solenoid S2 with respect to the solenoid S1. Now naturally the question will come, is there any relationship between M1 and M2? So basically yes, M21 is actually equals to M12. Okay, if you don't change the configuration, if you don't change the number of turns, then mutual inductance between two coils is constant. Okay, so no matter through which coil you are changing the current, okay, both coil will have same mutual inductance. For example, you are writing an answer paper in the exam. You know question number 1, your friend knows question number 2. You are writing question number 1 and you are helping your friend to write the same answer. Similarly, your friend is writing question number 2 and he is helping you to write the question number 2. So at the end of the exam, both of you will score equal number of marks. Now if unfortunately both of you know the wrong answers, both of you have written wrong answers, both of you will get 0 marks. So mutual inductance is same. So but after doing that, if you find that your friend scored highest marks and you scored 0 marks, that means your friend has cheated on you. He knows all the answers, he only taken the answers that he does not know from you, and he has given you the wrong answers. Even though if he has taken the correct answers from you, but still you have got 0 marks, means he has not even used your answers as well. So for just a joke, take it as a joke. So mutual inductance is between the relationship between two coils, okay, two mutually linked solenoids, two mutually linked coils. Okay, now the Faraday's law, from this Faraday's law can be written as the induced EMF can be written as minus M di2 by dt, or if this is when the current is passing through the S2 coil. Okay, or we can write this as sometimes we can write this as minus M di1 by dt when the current is linked to the first coil, okay, inner coil. It shows that varying current in a coil can induce an EMF in a neighboring coil. The magnitude of the induced EMF depends upon the rate of change of the current and the mutual inductance of the two coils. So basically it depends on the rate of change of current and the mutual inductance, both things. Okay, now let's look into a problem. Two coils have mutual inductance 0.005 Henry. The current changes in the first coil according to the equation I equals to Im sin omega t, where Im is 10 ampere and omega is 100 pi radian per second. The maximum value of EMF induced in the second coil. Okay, this is partly related to AC, but we can solve it without even knowing anything about AC. So current is given here, I equals to Im sin omega t. Okay, now we know that induced EMF is magnitude wise M di by dt. So what we have to do, we have to calculate di by dt. I is equal to Im sin omega t. So what is di by dt? So Im is constant. What is the differentiation of sin theta? Differentiation of sin theta is cos theta, right? Yes, cos theta. So what we will do, but there is a constant here, so constant will come out. So it will become cos omega t, right? So mutual inductance times Im omega cos omega t. Now if you read the question carefully, they have asked you the maximum value of the EMF. Now maximum value, when there is a sine or cos term is involved, and if they ask you what is the maximum value, in that case you have to take the maximum possible value of sine or cos. So in this case the maximum possible value of cos theta is 1. So the maximum value of cos omega t is 1. Right? So we just simply put this value here. So m is given 0.005, Im is given 10, omega is given 100 pi, and cos omega t is 1. Okay, so simply we will get how many zeros? 1, 2, 3. 3 zeros, 3 decimals. So simply it will become 5 pi. Right? You can do one more thing if you are confused how to reduce decimals still. So you can write 0.005 as 5 divided by 1000. Then hopefully you can cancel the zeros and you can write 5 pi. So the correct answer is 5 pi. Okay. Simple question, simple formula. So mutual inductance related formula, you know how to solve mutual inductance related questions as well. Now let's look into self-inductance. This is also very important. It is also possible that EMF is induced in a single isolated coil due to the change of flux through the coil. So as I said, I have one single coil, okay, and current is passing through this coil. If current passes through this coil, there will be a magnetic field produced by this current, okay, and this current, if you change this current linked with the coil using some mechanism, then this will in turn produce a magnetic field of that coil itself, okay, and this coil will try to stop the flow of the current that is happening through it. So basically it is like your mother is saying please go and study, and your inner self is saying no, I want to play PUBG little bit more, right? So that is the same thing happening to this coil also. This coil is saying the current is saying no, I have to flow through you. The coil is saying no, I have to play a little bit PUBG, so stop. Right? So that expression is given by similar to that of mutual inductance, but in this case only single coil is there, and it is written by epsilon is equal to minus L dl by di by dt. Okay, this EMF is called back EMF. Okay, this EMF, if the original current is passing in this direction, the back EMF will try to stop this current and it will produce a current in the opposite direction. That's why it is called back EMF. Okay, work needs to be done against this back EMF in establishing the current. This work done is stored as magnetic potential energy for the current I at an instant in the circuit. The rate of work done is given by work is basically half Li square. Okay, not rate. The work done is given by omega W is equal to half Li square. You can remember this. This is similar to half CV square. Okay, in case of self-inductance, it is half Li square. This formula is also very important. Simple one-line formula, and based on that, multiple questions come in your KCET exam. A solenoid of inductance, let's see one example. A solenoid of inductance 2 Henry carries a current of 1 ampere. What is the magnetic energy stored in this solenoid? This is also from one of your previous year questions. Okay, so what is the work done? That is the energy stored. Work done and energy stored are brothers. So if work is done, energy will be stored. So what is the energy stored? Half Li square. Okay, so the solenoid self-inductance is given by 2 Henry. Okay, current is given 1 ampere. So the energy stored is 1 joules. Okay, so the correct answer is 1 joules. Now to complicate this question, they might ask there are n number of turns, there are 10 number of turns. So in case of energy stored, it does not matter, because when you are considering this L, self-inductance, all the turns are already included in this formula. Okay, so to confuse you, maybe they will add number of turns, so don't get confused. Number of turns will not be used in this formula directly. Now another concept, AC generator. Now I have checked all the previous year questions. There was not a single question based on AC generator, not very recent, maybe very old questions maybe come from this concept, but in JEE sometimes they will ask this formula related question, but I will explain it anyway. An AC generator converts mechanical energy into electrical energy. Okay, the induced EMF for the rotating coil of n turns is given by, so we have, what is the structure, you can check in your books. There is a north pole, there is a south pole, and we have a coil, okay, inside passing through this. Okay, they have some connection over here, okay, some connection over here, and this is linked to a shaft. Okay, this is rotating. Now this may be linked to some fans, like your wind turbines, or some water turbine, hydroelectric power plant, or vapor turbine, okay, like in normal power stations. So different things are linked to this coil. Okay, now there are, in this coil there is not one single coil, there are multiple coils, okay, because one coil is obviously will produce very little current. So what is happening here, there are multiple coils here, but at the end there are two links, two ends coming out of this, and these are two very strong fixed magnets. Okay, these are two very strong fixed magnets, and when you rotate this coil rotates inside this. Okay, once this coil rotates, okay, there is a magnetic field, and we know that when there is a magnetic field changing in a coil, it will produce an EMF. Okay, that EMF is produced here, and that we collect from this thing. Okay, and then that is being supplied to our homes or to factories or to do some work. So basically AC generator is the main thing, that is the reason that we are getting the light from the power stations. Okay, AC generator is the main backbone of every operations that we are doing. Even if you are seeing this video, okay, till this point, then you are watching this video because there is an AC generator that produces electricity, that helps us to record this video, and that is used to transmit to you, and you are watching via mobile or laptop. That device is also powered by AC current, and that is being produced by somewhere by one AC generator. Okay, so epsilon is basically minus n d phi b by dt, and it can be written as NBA cos omega t, okay, or NBA sin omega t. Now what is this sin omega t? Sin omega t means there is a rotational motion. So rotational motion means there will be a sin omega t associated with the angular motion. Okay, so this is the angular speed of that this device. Okay, t is the time, and n is the number of turns, b is the magnetic field linked with the coil. Okay, a is the area of the coil, and omega is the angular speed of the rotation. So from this you can calculate the associated EMF with this coil. Okay, now time to homework. Don't forget to solve this homework and mention the answer in the comment below. You can pause the video here, answer these questions and mention the answer in the comment below. If your answer is correct, I will personally mention that your answer is correct. This is question number 1. Now this is question number 2. Pause the video, solve the answer question, mention the answer in the comment below. Okay, now all the videos that we are doing is available in a single playlist. You can go there, and you don't need to find all the videos in our channel. You just need to go to the playlist section and find this KCET 2025 physics. There you will get all the videos, all the latest videos till today, whatever we have done, everything will be available. If not now, it will be available by tomorrow morning. So you can check all the videos in this playlist, okay, that we are currently doing, and including the KPL. KPL will be coming this week. okay, Sunday. So don't miss the KPL as well. I request you to go to our WhatsApp channel, okay, and follow there. If you follow our WhatsApp channel, you can get the question paper from our WhatsApp channel. The link is given in the description. And if you like this video, don't forget to share it with your friends, like this video, and subscribe to our channel. Thank you for watching.